All right, so today we're going to be doing day 7 in Advent of Code. And today's first part of the challenge is that we get a bunch of numbers. And what do these mean? The left side is the total that we want to get if we do something to the right side. And in this example, in this problem, we can only add and multiply. So if we add 10 and 19, it's going to give us 29, which is not 190, so that's not good. But if we multiply them, we get 10 times 19, which is 190. It's the same thing. So then we're going to keep that to a total. So whenever we find a certain combination that is possible with these numbers, with addition and multiplication, then we're going to keep the total somewhere. And if there are several numbers, so in this case, there's 4 of them, we have to add addition, multiplication, or addition, multiplication, or addition, multiplication, and see, okay, if any combinations of the above yield in this answer. So there's 2 different approaches that we could do. We can either do an iterative approach, so we would make a for loop for this sign right here. So a for loop to either add a plus or a times, another for loop here inside that for loop to either add a plus or a times, and another for loop in that for loop as well to add another plus or a times. So that would be an iterative approach, but today actually I want to do a recursive approach. And to explain recursive a bit, I found this GIF. And if you imagine that the function is this guy right here, it calls itself twice, and then each function that has called itself also calls itself again and again and again and again. So it keeps calling itself, becoming smaller and smaller, and at some point it stops, okay? So there is some stopping point. It doesn't do this infinitely, of course, but there's a reason why we keep calling why it keeps calling itself. So I will show the code and it will make sense shortly. First, I will talk about how I parse the input file. So we get the file, we open it, and I give it to the read input function, which opens it, it reads all the lines, and then we want to put the parsed information into the equations list. That's what I'm going to do. So for each line that we find, we're going to split it at the 2 dots. So we see that the information on the left, which is what the result we want, is always split by 2 dots. And then the information on the right is just with spaces. But let's split it by the 2 dots first to get whatever's on the left and then whatever's on the right. So whatever's on the left goes to the target, and then whatever's on the right goes to numbers. And the numbers we have to work with a little bit more. The targets we just convert to integer and we strip it to get rid of weird characters. But then the numbers we have to make into a list because there's several of them. So we have to strip it and split it, and by default it is split by a space. So we don't even need to mention anything in the brackets here. And then we map it to integers and we give it to the list. And then what we want to do is to append them to the equations so that we just return a single thing. We don't have to do this. We could just return targets and numbers. We don't have to put them in equations. But since we can have list of lists, it's completely fine. It's no problem. So now that we return the equations, we will give it to calculate total calibration result. And what this will do is it will keep track of the total calibration result, which we will get by calling the evaluate equation function. And since if we find a certain combination that is right, let's say, okay, we find a combination that gives us this number, then we don't have to save the combination and whatever result it gives us, because the result should be whatever the target is. So we don't have to return the target, we already have it, and we can just add it to the total. So instead what we can just return is true or false, so that it goes in this if statement to be able to add the target or not. So if we go in the evaluate equation, we give it the target and numbers, but evaluate with pruning will have target, numbers, and then the first index or the 0th index. So if we look at a line that has not that many numbers, it will give it the 73 here. And then it will give it index 1, so just the number 1, and you will see why shortly. So this is the function that's recursive, right? And you can see that when it calls itself again, it sends the same thing, the numbers, the target, and then the index plus 1. Every time that it recursively calls itself, the index is 1 bigger. And the only the different thing that we do is that we take the current value and we add it to numbers at index. So numbers at index. Index was 1, so we're going to go to the numbers, and the index 1 would be 585 in this case. So we would be adding the 73 plus 585. And then it will call itself again, and then we will keep going, and there's not only the recursive part where it calls itself, but there's a stopping point. This is what helps it stop, and there's also a different stopping point, but this is for the pruning part, so that to make it a bit more efficient. And I will explain what pruning does in a second as well. So this checks if the current value is bigger than the target, okay? And why do we do that? Because I've made it so that it recursively calls itself with a plus first, right? And then with a multiplication sign. And why do we do that? Because, okay, if we have the numbers 2 and 3, okay, if we add, we get a 5, of course. But if we multiply, we get a 6. So even with small numbers, multiplication is bigger. So we want to check whatever gives us the smallest number. And then that's why I put the addition first. And of course, we have to be careful here, because if we get 1 and 1, the addition will yield in 2, but the multiplication will yield in 1 as well. So I've put a comment here that you have to be careful, but I've tested it with and without the pruning, and it seems that there is no instances where it wants us to multiply something with a 1 instead of add it. So it doesn't actually give us a different result. So maybe for your input, you would have to actually remove this pruning, so it will make the program a little bit slower. And what you could do if you still want it to be fast is you can make an if statement to check if there's ones, then to just be more careful and not always check this, and to check the multiplication and the plus even if there's a 1. So that's what you can do. And since we're checking if the current value is bigger than the target, we're checking, for example, if we add those two together, let's say that the target is 600. We added those two together, right? And then it's going to call itself again. And when it tries to add the third number, it's not even going to get there. It's going to be stopped here because it sees the current value is already bigger than the target. So if we only added those two first numbers and the value is already bigger than the target, then adding more numbers will only make it bigger. So we already know that it is impossible to get a correct combination. So we can just straight up return false. And then when we return false, it will not add the evaluate equation will also be false, and it will not add the target to the total calibration result, which is what we want. But if it does somehow reach this, which is index is equal to length of numbers, so if it called itself 4 times in this example, because we have 4 different numbers, this is what will happen. So the function is the f over here, okay? And then it will call itself with a plus. So it will add, and it will go all the way through. So first it will call this, and it will go all, this has to return something before this can even run. So for this to return something, it has to go all the way through, all the way through. So the function will call the plus side, which will call the same function with the plus side, which will call the same function with the plus side, which will call the same function with the plus side. You'll keep doing this if the current value does not exceed the target. So keep doing this until it reaches the bottom, so to say. And the bottom is whenever the index is the same as the length of numbers. So in this case, it's 4. And what will it do? It will check if the current value is equal to the target. If it's not equal to the target, so exclamation mark equals, that means not equals to, then it will return false. And when it returns false, it will return false up here. So it will return false to the first part, to the plus part. So it will not go in this if statement, and it will continue to this if statement. So it will go in the multiplication part right now. So it will try to do a multiplication in between one of the numbers. And if this returns false, then this whole function returns false, which will go here, and then we will be checking the multiplications again, and so on and so forth, and so on and so forth. So that's sort of how it traverses through the tree. And another reason why this prunes the tree is, let's say we somehow got in this multiplication, and then now we're going to the plus, and then we're going to go to the times, right? So if we're adding, and we already see that the current value is bigger than the target, right? Then multiplying will only make it bigger, right? So it's going to be even bigger. So we already know that it's going to be false. So we can just prune this entire node, and that's why it returns false, because it will go to its parent and then it will keep trying to do something else. So any children that this might have, any functions that it might call recursively again, it's not going to be able to call itself again. If this was 5 deep, then this one and this one and this one and so on and so forth, they will never be called because it was cut off right here. So these will never even be called. So without this thing right here, it will be a bit slower. That's all, and we will test later how much slower exactly. So this is the recursive function. If we run it, let's see what answer we get. We get 455 something something 288. So if we look 455 something something 288, and that is the correct answer. Now if we go to part 2, it is basically the exact same problem, but now we also have this concatenation operator. And what does that mean? If we have the numbers 15 and 6, we can do the concatenation operator to make it 156. So to put them together, sort of. So now instead of just addition and multiplication, we also have concatenation. So if we think in terms of this graph, the function, instead of just calling the addition and then the multiplication, let's say it's here, we will also have to call the concatenation operator, which is represented by these two vertical lines. So now it's going to be a lot more complicated, because think, every branch of the tree will have 3 instead of 2. So it will be 3 to the power of n, like how deep it is, instead of 2 to the power of n, which is going to be quite different. And that's why I was saying, if we had minus and then we had division as well, then we would have to have another branch and another branch. And imagine it's 5 to the power of n. That's a lot. And if n is quite big, then it will take a long time to run it. It just gets more and more complicated the more the more operators we have. But now we're just going to be working with 3 different operators. So let's see. Part 2. We do the exact same thing to read, but I've added one more thing because I actually want to test it now. Is it faster with the pruning or not? And by how much? And I've tested it a little bit, and it is actually about 30% faster with pruning, which is great. So the way that we can time it is we just import time in Python. We do time.time, which gives us the current time, and then that's at the start. And then whenever we call this function, whenever this returns something is when the whole program has already ran. So then when we get the result, the program has ran to completion. So we can just get the time again, and then that's the end time. And then when we minus them, we get just the second difference. So we will print this later and see what the difference was. So how long the program took to run. So the input is parsed the same, and then the calculate total calibration result is also the same. So what's different is not in here, but in evaluate with pruning. So the only thing that I've added is this little thing here, which is a third function. So it recursively called itself twice before. Now it calls itself 3 times. So it calls itself with the concatenated number. How do we do that? The current value and whatever the next index is. So 585 in this case. So we would take 75 and 585, and we would convert them to strings. So instead of being numbers, we convert it to strings, so that when we add them, when we do plus to a string, if I say FEL and then IX, it's going to concatenate it, and it's going to be Felix. If I do 1 and 2 and they're strings, if it's going to concatenate them, and it's going to be 1, 2. But they're not numbers yet, so we have to convert them back into numbers. So now it's going to be 12. And then it's going to give it to a concatenated value. And it's going to call the same function again with this concatenated value instead of the multiplying value or the added value, and then of course the index plus 1. So it's the same idea, but now the tree has 3 different branches every time that it goes down. And pruning is going to prove to be a lot more helpful. So before, when I ran this, okay, it runs in like 1 second, okay? Even if I put a timer, I don't think it's going to make a big difference. But if I remove this, we can see that it still takes about a second to run. So I'm not even going to bother to put a timer in this one. But in part 2, the timer is going to prove to actually do something. So if we run it without the pruning, right? If we run it, let's see how long it takes. I'm going to run it 3 times to see how long it actually takes. 6 seconds. It never took this long before, but recording probably makes my computer slower. So let's see. This is without pruning, so this should be the slower version. So 6.8 seconds, 6.4 seconds, and maybe 6 point something seconds again. So let's see. 7 seconds. Okay, so now we do Control KU to uncomment. It's Control KC if you want to comment something. Control KU to uncomment. Control S to save. And now we run it again with the pruning. So this should be faster. So instead of 6.8, 6.4, 7 seconds, let's see if it is actually faster. We will also run it 3 times. Now it's 5.8, so a little bit faster, 1 second faster. 5.29. Let's see if it can get even faster. It doesn't become faster every time, but it's just, we will take the average of this. So 5.34, so it's about maybe 1 to 2 seconds faster. When I wasn't recording, it was about 30% faster, from like 5 seconds to like 3.5, something like that. So that is the recursive function and the solution to the advent of code. Now let's talk about the time complexity. So if we say that m is the number of equations that are in the input, n is the number of numbers in each equation, and k is the number of recursive paths explored during pruning, then we can see that the time complexity is m to the times k, and since k is 2 to the power of n minus 1, then the time complexity in the worst case is m to the times 2 to the power of n minus 1. Space complexity is not too bad, but basically the time complexity is 2 to the power of how many times we recursively call ourselves, which is twice. My bad. We call it ourselves recursively 2 times, so it's 2 to the power of n minus 1. And then it's going to be the same thing here, except it's going to be 3 to the power of n minus 1. And if we had subtraction and division and to the power of and a bunch of other stuff, if there was 10 of them, it would be 10 to the power of something. And that would take forever to run probably. So these are the time complexities and space complexities. The space complexity is the same for the second one. And lastly, if you guys want to join the leaderboard, the private leaderboard, I will leave the code in the description. And yeah, thank you for watching. Happy holidays and see you tomorrow.